Hi viewers, welcome to this channel. Myself R. Prakash, working as Assistant Professor, Department of Mechanical Engineering in K.S.Rangasamy College of Technology. Today we are going to discuss about heat conduction through slab. So this is a typical arrangement of slab. So having a thickness L and having a temperature limits T1 and T2, and having the slab having a thermal conductivity of K. So the K represents the thermal conductivity of this material. Okay. So before we are going to derive this relation, we can able to know what is the basic law behind the conduction, right? So the basic law behind the conduction is the Fourier law of conduction. That Fourier law of conduction is nothing but it's the heat transfer is the directly proportional to the normal area and the temperature gradient. So this is the relation derived from Fourier law of conduction, that Q represent heat transfer in watts and K represent thermal conductivity. The thermal conductivity is nothing but the ability of material to conduct heat, right? So that unit will be watt per meter Kelvin, and A represent area, and dt divided by dx represent the temperature gradient. Okay, so this is the known values. Then followed by we can derive these heat transfer relations. So we simply rearranging the terms, that is q dx is equal to minus k into dt. Okay, I am simply multiplying the dx in the LHS side, that is q dx equal to minus ka into dt. Okay, so in order to derive the heat transfer relations, so we using the known limits. So in this case, this is a simple slab having a thickness of L. Okay, so the known limits will be 0 to L. Okay, for a thickness we have a limits 0 and the second limit will be L. So this is the two limits we have for a thickness. Okay, in order to temperature we have two limits, one is T1 and second limit will be T2. So using this known limit we can able to calculate the heat transfer rate of for this slab. Okay, now so integrating the above equation with the limit of 0 to L with the T1 to T2. Okay, so in order to integrate this thing, that is q into dx. So integral out of dx, that is 0 to L dx is equal to minus ka, that is the q and ka will be a constant value. So I am keeping outside. The integral of dt, that is T1 to T2, that is the limit. T1 and T2 is the temperature limits, and 0 to L is the limit for a thickness. Okay, so using these known limits, that is q into integral of 0 to L dx is equal to minus ka into integral of T1 to D2 dt. Okay, so now we integrating this thing, that is integral of dx is nothing but x. We are applying this known limit 0 to L, so L minus 0. Okay, so again is equal to minus ka. So integral of dt is simply t, and again substituting these known limits T1 to T2, that is T2 minus T1. Okay, again we rearrange this term, that is q into L. So L minus 0 is simply L, that is q into L. Okay, again we multiplying this minus sign here, that is ka into T1 minus T2. Okay, so in this case minus into plus, that is minus T2, again minus into minus plus, that is simply k into T1 minus T2. So this is the simple relation derived from integrating these known limits. We can able to know the values for heat transfer. Okay, for heat transfer is simply rearranging these terms, that is q is equal to ka into T1 minus T2 divided by L. Again we rearranging these terms, that is q is equal to T1 minus T2 divided by L divided by K. Okay, so this relation is simply we come into, that is del T divided by R. That del T represent the temperature difference of this slab, that this is del T. So this is the difference between these two temperature limits, that is del T, and this R represent the conduction resistance. Okay, so that R represents the L by Ka, that L by Ka is nothing but the conduction resistance of this material. So in this thing we can easily calculate the heat transfer through this slab using these known values, that is del T divided by R. So using this relation we can easily calculate the heat transfer through this slab area. So in few cases we can able to try the solve the temperature at a certain length. Okay, so for a slab having a 5 meter, so in order to we need to get the at 2 centimeter or 2 meter, what is the temperature at a particular watt. So in order to things we need to calculate at certain length, what is the temperature of this wall. So for that thing again we using the same limits at for in this case 0 to x and the temperature will be T1 to T. So using these two limits we can easily interpolate the same above equation into another relation, right? That is nothing but q x is equal to minus Ka into dt. So now in introducing these new limits, that is 0 to x and T1 to T. Again we integrating the above relation with the new limits, that is 0 to x into dx is equal to minus Ka integral of T1 to T into dt. Now the integrating the relation, so integral of dx is equal to x. Now applying the limits x minus 0, again minus Ka, integral of dt is nothing but simply t. Again we substituting the known limits, that is T1 to T, that is t minus T1. Again we simplifying the above equation, so x minus 0 is equal to x, so that is q into x is equal to qx is equal to, again the multiplying this minus sign in the brackets, that is Ka equal to T1 minus T. So this is the second simple relation derived from using the two new limits, that is 0 to x and T1 to T. So now as of now we have substituted two relation, so that is equation 2 and equation 3. It gives the two different relation with respect to two different limits. So first limit will be 0 to L and T1 to T2. This is the first limit. So using this first limit we can solve the equation 2, and then followed by using the second relation, that is 0 to x and T1 to 2. This is the second limit. So in this case we are solving the another equation, that is equation number 3. Okay, so using equation 2, that is QL is equal to Ka into T1 minus T2. Again we rearranging these terms, that is Q by Ka is equal to T1 minus T2 divided by L. Again the equation number 3, Q is equal to Ka into T1 minus T. Again we rearranging this term, that is Q is equal Q divided by Ka is equal to T1 minus T divided by x. So in this case, so both equation number 2 and 3, the LHS side remains same, that is left hand side Q by Ka. Again in equation 3 also Q by Ka. So interpreting these two relations, we can able to derive, that is T1 minus T2 divided by L is equal to T1 minus T divided by x. Again we rearranging these things, so temperature in LHS sides and thickness in RHS side. So again T1 minus T is equal to divided by T1 minus T2 is equal to x divided by L. So this is a simple relation derived using these two equations, that is equation 2 and equation 3. Okay, so using this relation we can easily interpolate at any point we can able to calculate the temperature at the particular wall or particular slab. Okay, so using these two things we can solve one problem. So that is the calculate the rate of heat loss for a red brick wall of length 6 meter, height 5 meter, thickness 0.3 meter. The temperature of inner surface 130 degrees Celsius and that of outer surface is 50 degrees Celsius. The thermal conductivity of red brick K is equal to 0.8 watt per meter Kelvin. Also calculate the temperature at the interior point of wall 25 centimeter distance from the inner wall. So this is the simple problem. So in this one we need to calculate two things. So one is how much amount of heat will be lost from this slab, that is a red brick wall, and second case is at 25 centimeter from the inner wall, what is the temperature lies in this red brick. Okay, these two things we need to calculate. So in this case, so this is a red brick wall having a length 6 meter and height 5 meter. The thickness of this red brick is 0.3 meter. Then the inner surface temperature is 130 degrees Celsius and the outer surface is 50 degrees Celsius. The thermal conductivity of red brick will be 0.8 watt per meter Kelvin. So in this case, first case we need to calculate the heat transfer rate, right? That is Q is equal to del T divided by R. So del T represents the temperature difference, that is T1 minus T2, that is 130 minus 50 divided by conduction resistance, right? That conduction resistance is nothing but L divided by Ka. The L represents the thickness of this material and K represents the thermal conductivity of this material and A represents the area of this material. Okay, so we substituting the known values, that is T1 equal to 130 and T2 is equal to 50. then L is equal to 0.3 and thermal conductivity is equal to 0.8, and the area is nothing but the length and height of this material, right? The length will be 6 meter and height will be 5 meter, so that is 6 into 5. So in order to we can able to calculate the total heat loss, that is 6400 watt. So in terms of kilowatt, simply 6.4 kilowatt. So then second case, in this problem we can calculate the temperature at interior point of wall 25 centimeter distance from the inner wall. That is, this is the interior point from 25 centimeter from the inner wall. What is the temperature lies in this wall? So this is the case number 2. So using the known relation, that is T1 minus T divided by T1 minus T2 is equal to X by L. So in order to substituting the known values, that T1 is equal to 130 degrees Celsius, again T1 is equal to 130 degrees Celsius, and T2 is equal to 50 degrees Celsius. So X is a certain distance, that is 25 centimeter. In terms of meter, that is 0.25. So with respect to length, so that L is represent thickness of this material. The thickness will be 0.3. So substituting these known values, the only unknown term is that temperature T. So that T gives the intermediate temperature at 25 centimeter from the inner wall, that is 63 degrees Celsius. So in this way we can easily calculate the heat transfer rate as well as the intermediate temperature from the known relations. Okay, so this is the outcome of this relation. So keep learning and growing. Thanks for watching. Thank you.